getting some muscle. All right, welcome back. Math 131, Lecture 16. We were having fun at the end of class yesterday. We were looking at integration by substitution, mixing section 6.1 and 6.9 to get and 6.1 and 9.1 together. This is extremely important for mastery, for success. Then we're going to come back and finish working 6.2 and 6.3. What happens is we learn integration. We just learn what to do. But we need to put some meaning to it. How are we going to apply it? What good is it, that we can just do these little calculations? So Riemann sum starts to put meaning to integration, and then that leads into the definite integral, and then we'll be headed in the direction of more applications of integration. Alrighty, so yesterday we were just playing with x to the r. So yesterday we were looking in section 6.1, the variable x raised to the r dx. And remember, r was not equal to -1. And that equals x to the r plus 1 over r plus 1 plus c. When you're integrating or anti-differentiating, you are given the derivative. You are looking for the function for which that is the derivative. Then in section 9.1, we said not all functions are the variable x raised to the r, but sometimes it's a function of x raised to the r, where u is a function of x. And this is where our chain rule and general power rule is being used in reverse. We have to take whatever our integrand is, convert it to u so we can make it real easy. We have to also be able to have a du in it, where our goal is to work it to this direction. Because if we can have integral of u to the r, you're integrating with respect to u, then it's u to the r plus 1 over r plus 1 plus c. All right, at the end of class yesterday, I threw out a big challenge to check out those critical thinking skills, and I was very pleased with the response I got. Let me go back over that. You're not raising your hand, are you? Let me go back over that in great detail, and then we'll have some more fun. There's a little pattern. I know I went over it, but it was kind of quick yesterday at the end of class, so we'll do it again. There's a little pattern you normally go through, so if you always follow the steps, follow the cookbook, it seems to work right out. Now, I also must tell you that you're only going to learn three simple types of integration, but there's tons of types of integration, other integration techniques, and there are books with tables, and you have software that does things, but we're very selective here in what we're getting. All right, that's just in case somebody taking this has already had calculus before and they think I'm not telling everything just right. Okay, this is not all there is to the story. All right, what you noticed yesterday was that you had some function raised to a power. It was not x raised to the r. So what we wanted to do was make a little simple substitution so life would be easy. So we just said, well, let's let u equal 3x squared plus 1. So what I say is come right under, I'm going to number the steps. There's number 1. So we're just going to come right underneath and make that substitution. All right? So we just came right underneath because you got to have everything lining up. Every little thing's got to line up. All right. Step 2 says, well, I've got to line something up with the x dx. And the only way I'm going to find a dx when I've got a u, which is a function of x, is to come back and take the derivative. So step 2, in all cases, I'm scared to say all, generally, will be to come and take the derivative of u with respect to x and get 6x. All right? And my goal is to get a dx. I don't want a dx in the denominator because I've got to make some substitutions over here. So the next step, of course, is say that du equals 6x dx. We just multiply both sides by dx because I need a dx in a numerator. Okay? All right. Now, this is the place, once you get this far, Step 4 is where you open your eyes. You're looking all directions. Okay? All right. Because you are looking at how can I replace x dx in terms of numbers and u's. I can't mix u's and x's. It's like you're taking English, converting it to Spanish. All right? You wouldn't want to take a paper that you were supposed to write in Spanish and have it broken up with English and Spanish. That would be like combining your u's and x's together. So we're going to go all the way to Spanish or whatever. All right. So when I look both ways, I've got to find a perfect replacement for x dx. And when I look right here, I'm also happy because there's the x dx that I need. If it's not there, that's another integration technique in another course. Okay? Or if it's not there on a test, it's a mistake I made. Okay? All right. So x dx is 1/6 du. That's step 5. Okay, you got to look both ways, and then you've got to find a way to make it match. So now we're going to come right under x dx and write in 1/6 du. Okay? All right. Now, just to make it pretty, nobody says you have to do this. I usually rewrite it 1/6 u to the 4th du. And in fact, if that 1/6 times the u to the 4th is getting on your nerves, you could actually write it as 1/6 times the integral u to the 4th du. All right, my whole goal was to get it with only numbers and u's and du's. Looks easier today, doesn't it? That's why I like to give you a little something one day and then come back to it another day. All right, so now it's a perfect u to the 4th du, so it's 1/6. And when you integrate this, it'll be u to the 5th over 5. Remember, you just add 1 to that r and divide by it, plus c. All right. Oops, so I guess step 6 was to integrate. You integrate it with respect to u. And then step 7, what is step 7? Yeah, the problem didn't even have a u in it. I used the u as a convenience for myself. So I got to go back and put what the u is. So that's going to be 1/30. In the place of u, I have 3x squared plus 1 raised to the 5th plus c. And that is the function. This is the function that if I come back and take its derivative, this part right here will be the derivative. Okay? Everybody good? Yes? Anybody have a question on this? All right, let me give you another one. I know you want a hard one, so let me think. Hard problem. Integrate. How hard do you want it? Not too hard? Okay, not too hard. Let's make that a cube. Let's make that a 4th. I'm looking for something that the numbers are all different. All right, so the integral of x squared divided by the quantity 5x cubed plus 1 raised to the 4th dx. That's a 4 there. All right, go for it. Follow the same process over and over and you'll get it. Would you make the whole thing your u?
No, wait.
What's your u? You need to write that out because that's really not equal to that. Be sure you use good steps there, good communication skills. What's your u? Okay, u is the main part of the problem that's raised to a power. So would you include the x squared there? You're looking for, what's the main idea? What's the major emphasis? Okay. Oh, you're just rewriting it?
Yeah, that's
okay.
So how do you know
You're
which
good.
one to make? I just guessed though. How do you know which
Well,
one
it's
to make
usually
it?
the most complicated part of your integrand. The most complicated part. You were doing great. But what's your u? Okay. All right. What's step 2? Mm-hmm. What's step 3? Okay. Okay. What's the next step? Use my glasses. What are you going to do? Look. Do you see? You got to. What else are you lacking in here? Replace. Write that dx in there. Okay. Now what's got to be changed over? The x squared and the dx. Do you see anything right there? See, you can do it. You are good at this, aren't you? I need to have you teach it.
So once I get to that part,
Mhm.
that dx matches, so I just do 1 over the whole thing to cancel it out? Is that how it works?
Well, rewrite your problem. Integral.
Right. Oh, now I'm rewriting it. So it's with that. Well, I got that much of it.
I know, so just write all that part down there and look and see what you have to replace. Do your integral sign. And put your dx there. Now, what's not acceptable in here? The x squared dx.
Right. Oh, and the x squared.
Mm-hmm.
Okay.
You almost have to put in every little step or you're going to get lost in it. But I'm seeing very good things. Very good things.
I'm stuck.
Stuck? Let's see where you're stuck.
That's the 5th step.
Was the... Oh, you looks like you got the looking going on. All right, let's
Yeah.
look at this.
I put my little look.
I know. You're good. All right. Can everybody see this? I'm going to make a little bit of editing on this, and then it becomes very clear. You called your u this, perfect. You found your derivative, perfect. Now, when you name your u, you went back and put it in, but you left off an important little part there. You don't want to get sloppy on this because that's where you're going to have some confusion, I think. So when you made your u substitutions, you came right in, put it in there just like it was supposed to be. Now, you took your derivative, and when you got right here, the reason you're looking at this and this is the x squared dx has got to be replaced. And when you look at this part right here, where you see the x squared dx?
Right there.
Right there. So by putting that there and going, okay, this is like Spanish and English mixed together, I got to find a replacement for the x squared dx. You can come right here, and now you tell me what the next step is.
15 x squared times dx.
Right, and how do you get x squared dx by itself?
Divide by 15.
1/15 du is exactly x squared dx. Everybody good there? So now, because this is the English and Spanish all together, we're going to have 1/15 du. I'll just put that right there. And then we have a 1 over u to the 4th. Okay? Now, how did you integrate like 1 over x to the 4th when it was just x? What's your step before you get ready to integrate this? It's got to be u raised to the r, not 1 over u raised to the r. So you have the integral 1/15 u to the negative 4 du. And now it's looking easy, isn't it? All right, so as I walked around, you're not the only one that did this. This is why I'm so somewhat glad that when I used your paper, you didn't do it, because I was noticing other people didn't do it either. When you make your substitution, you got to be careful to put in every little part and look at what you have. And your goal is to get it only with u's and du's. All right, is that better, everybody? Okay, so let's go with it. That would be 1/15, and now we got a u to the negative 4 du. We're going to add 1, so that would be u to the negative 3 over negative 3 plus c. All right, but that was not the original problem. We converted it to something simple. We now have to go back with what u really is. Guess 15 times negative 3 is negative 45. Negative 1 over 45, and u, we can put our u in the denominator. 5x cubed plus 1 cubed plus c. And there we are. Okay, brought the u to the negative 3 down in the denominator. And 15 times negative 3. Okay, everybody good? I think you can do it. All right. Next example. Okay, be sure you write down everything. Thank you for letting me use that. All right, here's the next example. I'm going to change on you a little bit. In 6.1, we integrated e to the x dx. What is it you take the derivative of that gives you e to the x? Okay, e to the x, and then we have plus c, right? All right, in 9.1, we're going to have the integral of e to the u du. We're integrating with respect to u, where u is some function of x. All right, and if you can get it in the form e to the u du, life is great. It will just simply be e to the u plus c, correct? All right, let's have a confidence builder here. I want you to integrate e to the 5x dx. How do you know you're going to need to go with section 9.1 on this? It's not e to the x, but e to a function of x. Actually, 6.1 has you memorize the formula, but I didn't see any reason to memorize it when it's this. Okay, so integrate e to the 5x. You know what your u is. You're trying to match it up, right? Match it up. Hint, what's your u? Do you see an e here?
Yeah, I see it. I just thought it was going to be hard.
I told you this was a confidence builder. I'll get to the hard ones. Give me a chance. I know you don't trust me. Have you got it? Well, yeah, I'm going to give you a little hint. Do you see this e right here? Do you see that 5x? All right, go for it. Just like before. U, replace, derivative, multiply by dx. Look both ways. Make the substitution. Integrate. You got it, Carrie? Write it so we can read it and pass it up here.
What do I write at the very last part? Like, front of the equal sign, what am I supposed to put? Not
Actually, you just go, this
Equals.
integral equals that, but it really is what is the function y, where this is the derivative. So it really is the function. But tradition has it, you just go equals. So you got it?
Let me see. Yeah, thanks.
You pass it up. All righty, let's look at it. All right, e to the 5x dx. And you figured out all by yourself that the u is probably 5x. So you came right underneath and you put in your integral sign, you put in your e, you put in what 5x was u. Then you came over here, this was step 1. Now step 2, always, is go find the derivative. And you found that du dx is 5 dx. And at that point, you looked both directions. And you knew you had to find a dx. You found that dx is 1/5 du. It's du over 5 or 1/5 du. A lot of people see it easier that way. And so in the place of dx, wait, you can't put a du here yet because you hadn't really made that substitution. Okay. So in the place of dx now, you're coming down here and replacing it with 1/5 du. This is e to the u times dx. So everything in here is multiplied. And now, oops, you changed it on me. Whoa, you're really mixing your Spanish and English. All right, so now you have it all in terms of numbers and u's. And so when you integrate, you kind of skipped a step on me. It's 1/5 e to the u plus c. But the problem was not with u's, and then you come back here and replace it. So in the end, you were fine. You were not technically perfect in every way, all the way coming down.
Just excited.
You were just excited. Okay, smiley face for you. Excited. All right, everybody good? Everybody got it? Let's beef it up a little bit. Because you were disappointed that I had an easy one.
No, I definitely got it wrong.
Okay.
I thought it was easier.
Okay, let's send it back. All right, I'm only working you on, I'm telling you what it is so you don't get the wrong one. Now, eventually you're going to have to figure out, is it a u to the r, is it a e to the u, or the other one, which is going to be a 1 over u du. You'll be making the decision. Right now I'm kind of spoon feeding you. All right, we won't go too, you don't want too hard. Okay, not too hard. So, we will have x e to the 3x squared plus 1, and then dx. The 3x squared plus 1 is the power here on the e. So it's the integral x e to the 3x squared plus 1 dx. The hint is it's an e to the u problem. perfect. Can I use yours? Everybody feeling good? Answer is yes. Some of you just don't know you feel good when you do. So I had to help you out there. All right, everybody got it? All right, make me proud. All right, let's see if we need to do any editing here. Let me get the red pen out just in case. All right, we notice that we have the natural exponential function raised to a complicated power here, which is some other function of x. So it's a good hint on a test that we have a u being the 3x squared plus 1, e to the u. If you pick the wrong thing, you're going to know it because when you try to do substitutions, it's not going to match up. All right, so as soon as she decided that this was going to be the u, she very carefully put everything in with the u. Okay, but this is x's and u's all over the place, so that tells you there's more to this substitution. The next step is always go take the derivative, and you know you're going to have to find a dx anyway, so you multiply both sides by dx, and then this is the place where you look both directions. That's not the nose, that's looking. Okay? All right, and there's a x. Did you care if I wrote all over your paper? I'm sorry. X and a dx. And here's an x and a dx, so multiply both sides by 1/6. Now the entire x dx goes to 1/6 du. You already had the e to the u. It's now a perfect e to the u du problem, so it's 1/6 e to the u plus c. Of course, that was not the original problem. Remember to substitute back, and we have a big check, and we'll write perfect in every way. All right. How many got that right? Made me feel good. Okay, we're trucking now. Now you'll let me make up some hard ones, right? All right. Ready for a hard one?
Yes.
Thank you. Okay. A hard one. Whoops, I was about to make that too hard. That's not going to work. Okay. I'm having trouble thinking of a hard one. All right, the integral of, okay, here we go. E to the x over 1 plus e to the x. Oh, that's not a good one either. Next one. I want to use that problem, but not with this example. Sorry. Integral of, okay. E to the 1 over x squared dx. All right. The integral of e to the 1 over x divided by the whole thing x squared dx. All right. That's about as hard as I can think of. Let me look up in the book and see if we can find something harder. wrote that down with confidence. Can I use your paper? Now, once you integrate it, you don't have that symbol there anymore.
So up to when? Okay, so integration is when you substitute something in?
The integration is you're looking for the function for which this is the derivative, and once you have found it, that symbol is not there anymore. Just put an equal sign. Because see, from here to here, you integrated it, right? Oh, well. Oh, wait, that symbol's not there either, because from here to here, you integrated it.
So this symbol's only when you're...
Right, that says this is the derivative. Once you find the function, the integral sign is gone. Okay? Hard.
Just to let myself know.
Yep. Alrighty, let's see how you're doing. First of all, for some people, the division is just a hang-up. So if you prefer, you can write this as e to the 1 over x times 1 over x squared dx. All right, and for a lot of people, that looks easier. Okay, it's up to you. All right, so here's the work we might or might not edit. Okay, first of all, I don't remember putting that on the paper. Do you see it? Hard. All right, check. It was hard. All right, first of all, it looks like you're trying to make a e to the u du type problem because you see an e in there. So the u part is 1 over x. So she came right underneath and put the u there. The concern is that you still have a x squared in the denominator with a dx. So the next step is always take that derivative. Now, remember, do you care if I write all over your paper? When you have u equals 1 over x, before you can take the derivative, you need to write it as a x to the negative 1. Derivative, decrease your exponent. Remember that yesterday? Du dx, we bring down the 1, negative 1, rewrite, and decrease by 1. So you get negative 1 over x squared. All right, so she got her negative 1 over x squared, multiplied both sides by dx. Multiplied both sides by dx. Very important step, number 4. Can you see it? Focus in on that one more time because that's so important. Can you? All right. Looking all over the place. Thank you. You guys are good, good, good. All right. So when you came back up here, you had a x squared, a dx over x squared, and the problem here is there's a negative. So she multiplied both sides by negative 1. So dx over x squared is negative 1 du. She made that direct substitution there. All right, so you integrate. When you integrate, you now say this is the function. So you don't continue with the integral sign. The integral sign says this is a derivative. Now I have found the function. So when you integrate, you get negative 1 e to the u plus c. All of this part right here was for our convenience. It's called u substitution. The function for which e to the 1 over x, x squared, is the derivative is minus e to the minus e, negative e to the 1 over x plus c. Perfect. Yes, you got it? Good, good, good. Everybody happy? All righty. Great job. Send that back. All right, we're ready to move to the next type then. All right. So far, and the fun part is we're going to treat it like a game later. What form does it fit? And then you integrate it. Okay, so far we've looked at u to the r du. That's where r is not equal to negative 1. We've looked at e to the u du. And now we want to look at the form the integral of 1 over u du. 1 over u du. And that's the case if you had a u to the r du. If the r was negative 1, that gives you that 1 over u du. So what is it you take the derivative of that gives you 1 over u? What do you take the derivative of that gives you 1 over x? Natural log absolute value, and then we have u plus c. Okay, so if it's a 1 over u. Now the hint is going to be, if you see a denominator that's a function and that entire denominator is raised to the first power, the denominator is raised to the first power, then that's a hint that's probably going to be a 1 over u. For example, the game, which form, if I had the problem 1 over x plus 3 to the 10th dx versus the form 1 over x plus 3 dx. All right. If you have 1 over x plus 3 to the 10th or 1 over x plus 3 dx, which form do you think the first one's going to fit of these three? If you rewrite that, that's going to be to a negative 10 power, right? So which form does this one fit? It's going to have to fit a u to the r, because you're going to have to rewrite that as a x plus 3 to the negative 10 dx. Okay? Which form is this going to fit? Well, this whole denominator is to a first power. This is a u to the first power right here. If you tried carrying it up to the numerator, you'd have an x plus 3 to the negative 1 dx. R can't be negative 1 for this formula. Okay? So the hint is, if you have the entire denominator as some function raised to a first power, it's a good chance it's a 1 over u to the first. Okay? All right, so let's try one. Actually, these will all be 1 over u du's, and then we'll mix up. All right, so your hint is, your big hint is a 1 over u du, which is natural log absolute value of u plus c. All right, the integral, and you want to start easy or hard. I'll let you call it because you don't trust me. Easy or hard? Easy. Okay, here we go, easy. Does it have to be real easy?
No.
Okay, not real easy. 1 over 2x plus 3 dx. All right, so you're supposed to integrate 1 over 2x plus 3. Did that help? Or were you past that?
No, I was just contemplating my moves. before I started.
Contemplating your moves. I like that. Carl, how you doing? Can I use your paper this time? Good. I feel like you lost something. What is you?
I plug that back in, that's 6 plus 3, and then I multiply 2 right there.
You can't distribute that 2
No,
through
you
there.
can't.
Okay, put what your U is. That's what you meant to do.
You're right, Steve.
That's because I was standing over you.
You just do it.
Did you say you just do it? That's like the Nike commercial. You just do it. Just do it. Okay. I find that students sometimes think it's a little clearer If you realize you have a function in the denominator, just put parentheses around it and raise it to a first power, and that will help give you a little hint. It might be a 1 over u to the first du problem. Okay, so here's the problem. We're going to see if we can edit, if need be. Of course, I have to use red ink so that you know you're getting your money's worth. All right, so the first thing you did was you put u equal 2x plus 3. You came right underneath. You sort of skipped a step on me. That's okay. You then realized there was still a dx up there. So you took the derivative of u with respect to x, which was 2, and then you multiplied through by dx. All right, then you looked both ways, and you saw that you needed to replace a dx, so dx is 1/2 du. So in the place of dx, she put her 1/2 on the outside of the integral sign, and there's the du. Is everybody happy this far? Okay, so now it's a perfect 1 over u du problem, so it's 1/2 natural log absolute value of u. Notice you don't have an integral sign anymore because you have now found the function for which that is the derivative. And so she just recopied her problem there to make a good mathematical statement. 1 over the integral 2x plus 3 dx is equal to 1/2 the natural log absolute value 2x plus 3 plus c. Perfect. Everybody good? Okay. Can we beef it up some now? All right, let's beef this up. The integral of e to the x over 1 plus e to the x dx. The hint is it's a 1 over u du problem. You always go to the most complicated looking function. And 1 plus e to the x is more complicated than e to the x. Okay, I'm watching your pen and I'm seeing everybody that I'm seeing get it correct, so I feel good. All right. I rewrote this as 1 over 1 plus e to the x times e to the x dx, again, because some people, when you have a fraction, feel better with multiplication. And the thing that you notice is that you have a denominator here raised to the first power. And you notice that this is more complicated looking than the other factor, which is a e to the x. So you might try u equals 1 plus e to the x. Come right underneath, 1 over u. Now we're going to have to replace the rest of that, so we'll take the derivative. And this is, Carla skipped a step, and that once you do enough of these, you realize you really can skip the next step. Instead of writing du dx, go ahead and write du equals, and the derivative of 1 is 0, the derivative of e to the x is e to the x, and then go ahead and mentally multiply. So you can start to skip a few steps if you're careful. This is where you look both directions. That's a perfect du. So when you integrate that, it's a natural log absolute value of u plus c. So our integral, e to the x over 1 plus e to the x dx, is equal to the natural log absolute value 1 plus e to the x plus c. All right, that is the function for which this is the derivative. Everybody got it? Good. Now, I keep talking to you about the more complicated looking function, but let's just analyze what we're really saying. I want to tell you just a little bit at a time. When you have the integral u to the r du, you've got to have a u, and you're going to have its derivative multiplied there. So really, when you look at your integration, you're looking for a function, and you're looking for its derivative also in there. So when we go back to the previous problem, you were looking for a function, and you were looking for its derivative. Here's a function, a big function, and there's its derivative. Earlier, when we had this problem, here is a function, and except for a number, a constant. There's its derivative right there. The derivative of x squared is 2x, so there's part of its derivative right there. So inside the integrand, you're looking for a function, and you're looking for its derivative. That's the way some people like to look at it. All right, so you have u to the r du, r not equal to -1, 1 over u to the first du, and you have e to the u du. All right, we're ready to play. What form does it fit? This is form 1, 2, 3. All right, this is like a game show. All right, we're on page 455. Page 455, section 9.1. All right, we're going to name the form that it fits, and you tell me what the u is. Okay, I'll try to move the book around so we can get in on that. Can you guys see that? There you go. All right. So it's the forms are u to the r, 1 over u, or e to the u. Now, when you look at that first one, would you even consider an e to the u? No. All right, so sometimes it's process of elimination. Would you consider it to be a 1 over u? No, because there's nothing in the denominator. So now, hey, we figured out what the form is. What is it? U to the r. All right, tell me what the u is. Yes, x squared plus 4. So if the x squared plus 4 is the u, remember du is going to be part of that derivative, and the derivative of that is really a 2x. And do you see that 2x sitting right there? Start to identify that. All right, look at number 2, and in 2 seconds I'm going to ask you what form does it fit. Okay, what is it? U to the r. You don't see an e in there. You don't see a 1 over u. And you have a function raised to a power. And by the way, what's the derivative of that 2x minus 1?
2.
2. It's just a 2. And there it is sitting right there for you when you follow through. Are you visualizing it? All right, let's go to problem number 3. All right, I'm looking for a function, and I'm looking for its derivative. All right, what can we eliminate right away? E to the u, because there's no e's in there. So this is either a u to the r or a 1 over u to the first. It's going to be a u to the r, because what's the degree in the denominator? 1/2. Okay? And then when you look at that u part, when you look at that, what you're calling a u part, what is the derivative of x squared? 2x, and the derivative of x? 1. Do you see how it's going to work out? All right, let's go to problem number 4. Half the battle for u substitution is recognizing it. All right, what did you eliminate immediately? E. There is no E. Then there's no denominator. This one's way too easy. What is it? U to the R. Which one's my U?
X squared plus 2x plus 3.
So there's my U. So you get it, take its derivative, and then look both ways. All right, I'm going to wait a half a second or longer on 5. What? That's going to be a e to the u. If you look at that u there, its derivative is 3x squared. What's sitting right there? Part of that. Do you see it? All right, number 6. It's an e to the u, isn't it? You guys are doing good. Number 7. Is it a u to the r? Yeah, there's no division, so it can't be 1 over u, and there's no e's, so it can't be an e to the u. And really, it's just 4 minus x squared to the 1/2, and the derivative of that is minus 2x, and there's your x that you're going to need right there, x. Okay. What about number 8? All right, if you think it's a 1 over x, the problem's going to be, or 1 over u, is you've got this numerator here that's pretty complicated. What is the derivative of 1? 0. What's the derivative of natural log x? 1 over x. Do you see that? So it's 1 plus natural log x quantity cubed times 1 over x dx. What form does that fit? U to the r. Okay? All right, number 9, that's a fast one. What is that? U to the r. Number 10, that's fast. What is it? U to the r. 11, e to the u. It is an e to the u. E to the square root of x. What's the derivative of square root of x? Bring the 1/2 down, rewrite x to the negative 1/2. There's part of your derivative right there. Everybody see it? So that's an e to the u. All right, 13 is hard, maybe. Work it. Work number 13. You're looking for a function and you're looking for its derivative. See who's got this right. You're almost there, but the derivative of log of a function is 1 over that function times.
Oh, okay.
What's the derivative of log of a function? 1 over that function times the derivative of that function. Chain rule. Do you already know how to do this? You are doing good, good, good. You are using great critical thinking skills. You're getting every one of them right. This must be your area of expertise. You're going to get it.
Derivative that just ends up being 1/x, right?
Mm-hmm. All right, we'll do this one together because you got lots more to challenge you later. All right, for number 13, I am going to rewrite it like this. The integral of the natural log 2x all raised to the first times 1 over x dx, because that to me is easier to see. All right, I remember that the derivative of log x is 1 over x, so it makes me think that the natural log of 2x is probably going to be my u, and the rest of this will probably be my du, so it looks kind of like a u to the first du problem. All right, so let's come over to the side. U is equal to natural log 2x. Come right underneath, u to the first. The next step is always to take the derivative. Remember, you can use your chain rule here, or you could write this as natural log of 2 plus natural log of x using your properties. Properties of logarithms, natural log of 2 plus natural log of x. And the derivative of that is going to be 1 over x. Or if you do the derivative of log of a function, it's going to be 1 over that function times the derivative of that function. So it always comes out to be still 1 over x. 1 over natural log of 2x is 1 over x, the derivative. All right, so we'll say du equals 1 over x dx. We look. Let's do some serious looking here. This is the eyeballs looking. All right, serious looking. That's a perfect du. So it's a u to the first du problem. So we have u squared over 2 plus c. U is natural log 2x. We'll square that, put it over 2 plus c. How many got that? Okay, a few of you. A few of you. All right. Can I answer a question? I know it looks easier when I do it, doesn't it?
Wait, why is it squared?
When you integrate u to the first, it's a u to the r. Remember, you add 1, divide by it. If you checked it by taking the derivative of this, you'd be back u to the first. Okay. Remember, when you do a derivative, you're decreasing exponents. When you integrate, you're increasing i's. Okay. All right. Let's continue on with our game. What form does it fit? Getting the right form's half the battle, wouldn't you say? All right. Number 14. That's really a square root of the natural log x times 1 over x dx. What form do you think that is? U to the r. Okay, because that's a natural log of x raised to the 1/2 power, and then the 1 over x dx is the derivative. So it's a u to the r. The u is natural log x. All right, number 15. I'm looking for a function, and I'm looking for its derivative. Say it loud.
1 over u.
How did you know?
Because put parentheses around the whole bottom to the first.
Okay, the whole denominator here is to the first power, and you notice that its derivative is sitting up there in the numerator, right? So it's a 1 over u, and then the derivative of the x to the 5th is 5x to the 4th, so it's almost the whole derivative up there. Good, so it's a 1 over u. All right, how about number 16? How do you know it's a u to the r? The denominator is raised to the 1/2 power, right? It's not to the first. All right, number 17. It's a u to the r because it's raised to the 2nd power. 18, what is it? Yeah, because the derivative 1 over x is minus 1x to the negative 2. There's part of the derivative there. So it's a u to the 5th. Ooh, 19. What do you think about that one? It is going to be a u to the r. You might have to write that natural log of square root of x as natural log of x rate. Let me help you out on this one. This one looks bad. Well, I'm sure you don't need help, but I am going to just help you. When you have natural log of x and it's only the x raised to the 1/2, only the x raised to the 1/2 times 1 over x dx, how can you use your properties of logs to simplify here? What can you do with that 1/2? Move it in front. So you have 1/2 natural log x times 1 over x dx. So I'm looking for a function and I'm looking for its derivative. So if I have natural log of x to the first, if that's my u, there's my du sitting right there beside it. Do you see? So you had to use your properties of logarithms to simplify that before you could integrate it. Okay? Otherwise, what would happen? Well, maybe you could take the derivative of that. Let's see. If you, well, no, you couldn't do that. Yeah, it would still work. No, it wouldn't. Yes, it would. Yes, it would. Let's try. You suppose you say your whole thing is natural log of x to the 1/2. All right, the derivative log of a function is 1 over that function times the derivative of that function, which is 1/2 rewrite decreased by 1. Yeah, it still works, so you can't miss it. So either way, you couldn't miss it. If you use your properties, though, it sure made it easier, didn't it? So it's a u to the first du. Okay? All right. What do you think about number 20? What form does it fit? 1 over u, because that whole denominator is to the first. What about this 21? 1 over u. What do you think about 22? U to the r, because the derivative of natural log 3x is 1 over the 3x times 3, and there's part of that x in the denominator. Very good. 23, what do you bet that is? It is a e to the u. How do you rewrite e to the x squared to get it up in the numerator? You got to get it in the right form. So you have 1 over, 1 over e to the x squared times 8x dx. But I got to get it as a e to the u. So how are you going to rewrite this part right here? Okay, so if you put in every little step, it would be this raised to a -1, right? And then how do you handle power of a power? Multiply. So this will be equal to the integral of e x squared times -1 is minus x squared times 8x dx. So it fits a e to the u. Okay? E to the u. Everybody got it? Yes, you do. All right, number 24. Oh, that's too easy. What is it? U to the r. What's your r? -3. All right, 25's hard. It is a 1 over u. Let's try number 25. Aren't these fun? Yes. We just think if we all did them together on the test, what fun it would be. Number 25. Did you get it? All right, I'm going to push you a little bit because we need to get started in chapter 6, sections 2 and 3. For me, personally, I like to write it as a product so that I can see the different factors. And then I recognize that the natural log of x squared is the same thing as 2 natural log x using my properties. Okay, I'm just looking for ways to make it look easy. And if I do it like Carla does, she puts the 1/2 on the outside. Because it's just a constant and she doesn't want it getting in her way. All right, so I'm looking for a function u and I'm looking for its derivative. What function do you see that also has its derivative there? Natural log of x, because the derivative of natural log x is 1 over x dx. All right, so we'll let u equal natural log x. So we have 1/2 the integral 1 over u. Du is equal to 1 over x dx. The 1 over x dx is exactly du. So we get 1/2 natural log absolute value u plus c. So let's put in what it is. We get 1/2 natural log, in the place of u, we put natural log x plus c. Oh, whoops. No, it's not a, my u is natural log x. Log of the log of x is not, wait, what was your question or comment?
Yeah, I put u for ln x squared.
Okay, all right.
So that's what I did.
So if you use that as an x squared, you probably didn't have a 1/2 out here, did you? All right, so let's keep it the way you did it. You put, you went from here, and you said let u equal the natural log of x squared. Okay, so you would have the integral of 1 over u, and I still have a 1 over x dx to worry about. All right, so du, the derivative log of x squared is 1 over x squared times 2x dx. Okay, and let's see here. That simplifies to du equals 2 over x dx. So when you look, okay, so you get 1/2 du equals 1 over x dx. Correct. So you get the integral 1 over u, 1/2 du. All right, yeah, that's equivalent. It's equivalent to what I had apparently. So you get 1/2 natural log of u and u is log x squared absolute value plus c. Apparently, that seems really strange, doesn't it?
That's what I did. And
Am I missing something here? I didn't make any mistakes, did I? All right. I'll investigate that a little further and see if I'm missing something. The log of the log. It's hard to believe those two things would be equivalent, isn't it? Okay, I'll investigate it and get back with it. All righty. Let's move in back to section 6.2 and 3. And what we're trying to do now is to put some meaning to all this integration. And I will be back again on this next time too. All right, chapter 6, sections 2 and 3. We want to put some meaning to integration. We want to put some meaning to it. All right. First of all, I just want to give you something we already know so that I can relate it to our integration. All right, so what I want us to do is recall that if we have a triangle, all right, this is really going somewhere at this moment. You don't believe me, but it is. And I'm going to draw this as the line y equals 2x. But I'm going to make a little right triangle here, and I'm going to stop, say, at x equal to 3. X equal to 3. Okay? If I ask you what is the area of this triangle, we would just use geometry. The base is 3. The height is 6. The area is 1/2 the base times the height. And the area would be what, 9 square units? 9 square units. All right. This is going to be a simple example where I'm using a straight line to find and then converting it to a right triangle. Most functions that we're going to deal with are not straight lines. If you buy a piece of property, say this is the road frontage right here, usually when you buy a piece of property, it's not an exact rectangle. And you have to have a way for figuring up the area. This is called the area under the curve. So it could be a piece of property or something like that. All right. So if it's not a nice straight line, it's harder to do. So one way we can do it, and which is the understanding to get to the integrals, is what is called Riemann sums. Riemann sums. All right, and that's actually in section 6.2. All right, now what Riemann sums is, it says divided into little rectangles, divide into rectangles of equal width. And then find the areas of the rectangles and add. Okay, we're going to sum up the areas of little rectangles of equal width. All right. So what we're going to do is decide how we want to divide it up. And I'm going to just divide it up into 3 equal parts because it just makes it easier to do. All right. Now your book will say n subintervals. So in our case, I'm going to divide it up into 3 parts, so our n will be equal to 3. So we do this little delta x is equal to b minus a over n. This looks worse than what it is. A is where it starts. B is where it ends. N is how many divisions there are. So 3 minus 0 over 3. So that's going to tell me the width of each one of these little rectangles is going to be 1 unit, which you could figure that out the way I did it. Right? 1, 2, 3. All right. Now, we have 3 options for Riemann sums. One's called left endpoint, right endpoint, midpoint. All right, we're going to start with midpoint. We're going to use midpoint sums. All right, So what we're going to do here is we're going to go to the first little interval from 0 to 1. And I'm going to go to the middle of that interval. And I'm going to get a little x value there. Well, that's a half, right? Halfway between 0 and 1 is a half. And I'm going to go up here and get on the line y. And I'm going to find out what the y value is when x is a half, because this is going to give me the height of my rectangle. The y value is the height. Y value is the height. So I'm going to the midpoint of my interval, and I'm going to get the height. And I'm just going to draw a little line straight across. So this is going to be y equals 2 times a half, or 1. So the height of that rectangle there is 1. So what's going to be the area of my first little rectangle? 1 by 1. So we'll have 1 times 1 area of my little first rectangle. All right, let's go to the second little rectangle. Halfway between 1 and 2 is the point 3 halves, right? 3 halves is in the middle here. So we're going to go up here, and we got to get the y value, because that's going to tell me how high. So I'm going to look at y equals 2 times 3 halves. And so this height is going to be 3 units high. All right. So it's going to be like a height times a width. Okay, so in this one, the height is 3. And the width is 1. Okay? And now I'm going to go to the next little interval between 2 and 3. Halfway between that would be, what, 5 halves? Okay, so we'll go up here to get our height. All right, so y now is going to be 2 times 5 halves, which is 5. So the height is 5 and the width is 1. All right, now you can see that my little rectangles included some area, but it also left out some area. Included some area, left out some area. Included some area, left out some area. Now, because this is a straight line, I was very careful in what I selected. My answer is going to look good, really good, all right? But the idea is that if you put a lot of little rectangles in here, you really would not be including too much area or leaving out too much. If you put in 500 little rectangles in here, it would pretty much clean it up. All right, but I kind of knew what this one was going to do. So we have 1 plus 3 plus 5, and by using Riemann sums, it's going to be 9 square units. 9 square units. Okay, and that only worked because I had a straight line there. Okay, so that would give me an approximation to the area under this curve. An approximation to the area under the curve, which actually turned out to be exactly what it is. All right? Now, you're going, well, how does that all work related to the integral? You were thinking that, correct? How does that relate to the integral? All righty. This little integral sign right here is really a elongated S, and long time ago it was really meant to be a summing sign, a S for sum. And what we're really doing is, related to this picture, we are going to sum up all the heights times the widths of the million little rectangles that you can put under this curve, y equals 2x, from 0 to 3. So this says I'm going to sum up 1,000,000 little rectangles so that I fill up the entire space in here, starting at x, going to 3, height times width, the areas of 1,000,000 little rectangles. Now, we're going to sum them up from 0 to 3, the integral from 0 to 3. Now, how would I express the height? How would I express the height of every little rectangle for every value of x from 0 to 3? 2x, very good. Isn't 2x the y value? How tall every rectangle is? Now, the width, back on the other page, we use that to be delta x. All right, remember that when we started with derivatives, we'd have change in y's over change in x, and if you let that little delta x start to approach 0, it was pretty close to dy dx. That's the little itsy bitsy change in y or a little itsy bitsy change in x. So because our little delta x's in here approach 0, they're so teeny tiny, in the place of the width we put dx. Okay? All right, so we're summing up the areas of all the little rectangles that we can put in here whose heights are defined by 2x, whose widths are itsy bitsy dx's. All right, this is called a definite integral. Definite integral. As opposed to what we've been doing without any values here as indefinite integrals. This is called a definite. All right, so we're going to integrate this, and the answer is going to be 9. Just want to go ahead and tell you this. All right, if you integrate 2x, what do you get, everybody? X squared, because it would be 2 times x squared over 2, so you're going to get x squared. And we'll go ahead and put our little plus c in. Now, how do we deal with this 0 to 3? This is called the fundamental theorem of calculus. You might want to stay in Saturday night and entertain somebody and teach them about what the fundamental theorem of calculus is. What this says is we want to evaluate from x equals 0 to x equals 3. This little line here says evaluate from x equals 0 to x equal to 3. Okay, so if I said, what's the distance between 0 and 3, because I'm going to figure out the distance from 0 to 3, wouldn't you go 3 minus 0? What's the distance from 0 to 3? You go 3, take away 0, right? So evaluate from 0 to 3 says we're going to start with the 3, and we're just going to substitute it in. So we have, 3 squared plus c minus 0 squared plus c. So we put in the top number, 3 squared plus c, minus the bottom number, 0 squared plus c. All right, now what do you notice about those c's right away? They're going to cancel out. C, take away c. So a lot of people, when they evaluate a definite integral, they leave off the plus c, because it's always going to cancel out. But if you're scared you're going to leave a plus c off on the test anyway for the indefinite integral, go ahead and put it in there. All right, so 3 squared is 9. 9 minus 0 is 9. And there we have it. The value of the definite integral is 9. Okay? All right, I just told you a lot at one time. What was the question?
Oh, on the midpoint sums.
Uh-huh.
How come it's always just times 1 on everyone?
Okay, all right. The question was, why was this width times 1? Because when you're using Riemann sums, you're going to divide your rectangle into equal widths. And if I went from 0 to 3 and decided I was going to do 3 subintervals, my delta x, my width every time from 1 to 2 is 1 unit, from 2 to 3 is 1 unit. So all my widths are 1.
Okay, so the ends given.
You'd have to be told how many subintervals you're going to use. If my subintervals were 6, my widths would have always been a half. Okay? All right, so here's what I was trying to tell you to get you thinking, is that we're trying to put some meaning, one meaning anyway, to a definite integral. There are a lot of applications for a definite integral. But the first and the most basic is area under the curve. Area under the curve. And the way that was developed was by a good old man named Mr. Riemann. Too bad he wasn't a woman, but he was a man. Riemann. And what he said was, I should be able to divide these up into little rectangles of equal width. Now, he would have not made them big old ones. He probably would have used 0.1 width or 0.01, little itsy bitsy rectangles. And he found out that if he divided it into little rectangles of equal width and had enough of them, he could really find the area under the curve. And then realized that that also led right into the definite integral. So that was a great discovery there, that you can find the area under the curve using the derivative integration. All right, so Riemann sum says, and I only did midpoint. I'll come back next time and do left endpoint and right endpoint. Okay, so you get your widths. If we're doing midpoint, you're going to get the height of your rectangles by going to the midpoint of the interval and go up and get your y value. And then you just get the area of each rectangle, height times width, height times width, height times width. And you add them up. That is only going to give you an approximation. If you have a curve, you can only get so close using Riemann sums because you can't physically put in enough little rectangles. We have mathematical software that you could put in 5,000 little rectangles and get really, really close. All right, so what I wanted to tell you was we could add meaning to the integral sign. It means I'm going to sum up all the little rectangles I can whose height is defined by the y value, because y tells you height, and whose width is a little itsy bitsy dx. So this says I'm putting in so many rectangles, this whole area is covered. So we're going to sum up from 0 to 3. We're going to integrate from 0 to 3, 2x dx, heights times widths. Once you integrate, you're going to evaluate from 0 to 3. Put in your top number minus your bottom number, and that gives you the area under the curve. And this is the exact area under the curve, because this took in every little value of x going from 0 to 3. Okay? All right, can you have fun over the weekend with this? I want to see hear some enthusiasm so we can quit.
Sure. Yep.
Yep, you're going to have a great time. Have a good day, everybody.